afternoon to all. So
Good afternoon, sir.
Good afternoon,
yeah.
sir.
So let us discuss on the systems and their properties and LTI systems, and some of the properties like convolution and few important aspects of related to LTI systems that relates signals and systems. Okay, so mostly this will be the last review class on signals and systems and their properties. So from the next class onwards, we will discuss on the discrete time Fourier transform. And subsequently we discuss on the discrete Fourier transform and so on. Okay. So let us I will share the screen, okay, with the notes. Before I start a discussion on the systems, you let me know what say what is a system. Hello.
Interconnection of devices.
Yeah, it's interconnection of devices, fine. System. So here in this context, what do we consider as the system?
It is an entity which processes a signal.
Okay, that processes the signal. Very good. Okay. Yeah. So sometimes the system is the one which most of the times the system is that processes the signal or generates the signal. Okay, and it there may be several systems that may be interconnected. So that's where the interconnection of devices, etc., will come into picture, right? Just yeah, fine, good. So is this visible? Notes visible now? The blank page of the notes?
Yes, sir. Yes, sir.
Yes, okay. So fine, let us start the discussion. So as we said, a system is one which takes a signal and processes and gives some output. Okay, so usually it will have an input and an output, right? So now the question is, how do I denote or how do I represent a system? Okay, so now we're discussing on the discrete systems. So we discuss on the discrete systems. So how do I represent a system? Any some of can some of you give some pointers on that?
So through mathematical models.
Yeah, that's fine. Give explicit mathematical model. So one way of representing is you give some example. So when I ask you to give some mathematical model, you can give any example. So y of n equal to
T of x of n.
Okay, e of x of n. Okay, fine. So this is also fine. Okay, or to be simple, y of n equal to some, okay, some function of x of n.
That
Okay.
is what I said, sir.
Yeah, that is fine. So explicitly we write as a some function of x of n. Okay. So this is one way of representing a system. But are there any other ways of representing this system? So other than this x of n relating x of n and y of n, are there any other ways of relating the systems or representing the systems?
So through electric circuits,
Okay. For electric
like
circuits?
RC circuit.
Okay. RC circuit, it is fine. So you are telling visualization of the system. So finally you can get some, say, differential equation relating the continuous time systems like RC circuit or any other circuit, right? Or in this discrete systems, you get some difference equation or some expression relating x of n and y of n. Okay. And further, if we know some of the properties of the systems, then we will be able to represent it better. Fine. So if I say that if some properties we will discuss, anyway, the properties that we discuss are linearity. So what are the usual properties that we discuss in the context of systems? Linearity.
Stability.
Time in where?
Linearity and then?
Time in where?
Stability.
Time. Variant or invariant. Okay. And then what are the other properties usually we discuss in context of
Stability.
systems?
Static or dynamic?
Stability.
Yeah, causality. Okay, and stability.
Casualness.
Okay, these are the main properties, even though there are other things like memoryless and so on. So
Invertibility.
what is that? Reversibility. Okay,
Reversibility.
so reversibility, memoryless systems and so on. Okay, these are the main properties that we usually discuss in the context of systems. Okay, so say we try to discuss briefly each of these things. Then given that the system follows some of the properties like linearity and say time invariance, if I say that the system follows linearity and time invariance, then I will be able to represent the system better, right? Yes or no?
Yes, sir.
How do I represent if I say that the if the system is linear and time invariant, in what better way we can represent it? Can one of you tell?
Impulse response, sir.
Yeah, through impulse response of the system. So we will discuss that subsequently. So we need not even tell what is x of n and y of n. Okay, so we need not relate in terms of inputs and outputs. There is other way of representing it through impulse response directly. Okay, fine. Okay, so now let us start the discussion on linearity. So just yeah, how do we define linearity? So when we say that the system is linear,
If the system
yeah,
satisfies additivity and homogeneity.
Yeah, if it has the properties of homogeneity and superposition, then we may call it as the linear system. Fine. So so what do we mean? How do we test? Say, for example, if I ask you to test whether a system is linear or not. Okay. So what is the procedure to verify the linearity? I request some of those who have not answered so far to answer. So assume that I have given you a system. Okay, like this. And I just want to know whether the system, whichever I have given you, is linear or not. So how do I check it? Yeah,
So we can say system is linear if the output for a linear combination of the inputs, it is the same as the linear combination of individual responses.
Right, very good. Very good. So the x1 of n, if I give one input, if I get y1 of n, okay, and I give another input. Okay, this input has nothing to do with the first input. and I may get some output y2 of n. Okay, some linear combination of these inputs. So alpha 1 times alpha 1 times x1 of n alpha 1 times x1 of n, if I give as the input, or alpha 1 times x1 of n plus alpha 2 times x2 of n, if I give as the input, okay, so then the corresponding output what I expect is what? Expect is alpha 1 times
Alpha 1 times
y1 of
y1
t
of n
plus alpha 2
alpha 2
y2 of
times y2
alpha
of n.
2 times
Okay, so usually what
y2
will happen? So let I construct x3 of n like this. Okay, to verify the linearity, what is the procedure we do? Especially those who are not very familiar with this, is we give some input x1 of n and collect its output y1 of n. Similarly, give another input x2 of n and collect its output y2 of n. Now I formulate a third input x3 of n. Okay, so this is the formulated or a formulated input in terms of earlier two inputs. Okay, so I will formulate a input, x3 of n, okay, and give as the give to the system. The output I get is y3 of n, because x3 of n is given as input. Its output I get will be y3 of n. Now, if the system is linear, okay, is the check for linearity is this. Okay, if is this y3 of n equal to alpha 1 times y1 of n plus alpha 2 times y2 of n. Okay, so this should be very clear. Till here I just give inputs and collect outputs. Here I formulate the input like this. Okay, and then give it, and what I observe is only y3 of n. Now, after observing y3 of n, what I check or test for the linearity is it following superposition? That means combining two inputs if I give is still that, or the outputs are also exactly combined or not. And homogeneity. If I multiply by alpha and to the input, will the output also get multiplied by the same factor? Okay, so that is my check for linearity. Okay. So in general, what do you think of a linear system? So why linearity is a very important property. So this is fine mathematically, but what does linearity ensures?
Sir, we can predict if the system is linear.
Yeah, if this system is linear, what advantage we may have?
Yes, sir. If an input is applied to the system, then the output should also be similar to the input, and there should not be any
Yeah, that's fine.
other extra frequencies that are added in the output.
Okay.
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 And only a phase change is allowed in the output without changing the
Okay.
amplitude.
Okay.
But
Yeah.
linearity
So
we can
one thing that you can do is see if I know that the system is linear. Okay. So if I know response to one x of n, for example, I can know any of the alpha times x of n, or alpha being anything. Okay. So, and also if I verify with say x1 of n, x2 of n, I know its output, how the system responds. If I just test with a limited number of signals at the input, I will be able to tell how it responds to a large number of like linear combination of signals I have already tested with. Okay, it doesn't behave in a very different way. So if I know that, say if I push something, if it goes by epsilon times or alpha times, okay, if I push little differently from another way, it push by another, say some alpha 2 times, then if I push with both intensities, both hands or both pressures together, it goes only by alpha 1 plus alpha 2. It doesn't go to infinity. Okay, so it's like doesn't break in some sense. Okay, like that. So I can the behavior of the system for some of the signals. If I know, okay, how it reacts, I can tell for a large combination of systems for our signals how does it behaves. Okay, so in that way it is easy to predict the response of the system for a large class of inputs from the limited class of inputs I experiment with. Okay, initially. Fine.
Yes, sir.
So what is the next property? Yeah, what is the next property? So we will
Time
take a
varies.
small example here
Time
before we
invariance.
move on to the next property. So I will just give some of the systems here. Tell me quickly whether they are linear. Okay. So I request some of the majors to answer, army officers to answer. So x of n is equal to, okay, I am writing, not strictly writing the brackets in notation, but consider them as square. Okay, plus u of n plus 1. Is this system linear? Okay, the question is this system linear? Yeah, request one of the army officers to answer. What do you think?
Yes,
I'm
sir,
not able to-
it will be a linear system, sir.
Yeah, why? Okay, so we will just check. Okay, is this linear system? That's our question. Okay, so let us check. So those who answered, please let me know how to check this. So if I want to check whether this is a linear system, this is a system now given. Because see, if I specify input-output relation, okay, so it means that I have given a system to you. Okay, so now we want to check whether this is a linear system. Yeah, what should I, how should I start? Yeah. So I should give,
x1 of n.
yeah, I will give x1 of n. Okay, please tell, I request army officers to answer now, so that actually you will be clear. So output will be what?
Y of n, sir. Y1 n.
Y1 of n. But what is Y1 of n explicitly? Tell quickly.
It
If
will
you are
be
clear,
x1
you
n
tell quickly.
plus u of n plus 1. x1
very
n
good.
plus u of n plus 1.
Yeah, plus u of n plus 1. Okay, fine. Now complete the process. x2 of n I will give input. What will be the output?
Y2 n, sir. x2 n plus u of n plus 1.
x2 of n plus u of n plus 1.
u of n plus
Now
1.
what should I give as input? x3 of n. But what is this x3 of n? It should be formulated or composed of some linear
Maybe
combination of
x1 n
x2
plus x2 n.
Yeah, simply
Maybe a
to
sum of
give
these.
x1 of n plus x2 n. Okay, so to
X2n.
simplify my process. And what will be the output? Y3 of n will be equal
x1 n
to?
plus x2 n plus
No.
x1 n plus
Yeah,
x2 n.
I will better write in terms of x3 n, because that is where
Sure.
I will have a clarity. Okay, so
It is
x3
non-linear, sir. It is not linear.
it is now. So if I
Correct.
expand it, what is x3? x3 is simply
x1 plus
of n
x2. x1
plus x2
plus
of
x2
n
of n.
plus u of n plus 1. But will I be able to write this? Okay, can I write this is equal to, this is a question mark now, is equal to y1 of n plus y2 of n?
No, sir.
Can I write like this? No, I can't write. Okay, because it's not, because this is equal to x1 of n plus u of n plus 1. Okay, plus x2 of n
x2 n plus u
plus
of n.
u of n plus 1. Okay, so I will have this 2 times, which is equal to x1 of n plus x2 of n plus 2 times u of n plus 1. Okay, so both are not, they are not equal. These two are not equal. Okay, these two are not equal. Okay, so this is not a linear system. Fine.
Yes.
Yeah, yes. This is how you should do it. So what I request is, if you people have not yet started, those who have started, it is very good, fine. Okay, those who have not started, please complete the assignments that I have given quickly, so that actually you will face all these, say, even though you may know concepts like in some details, when you do the problems, new doubts will come. Okay, see, if you think in terms of a purely like a conceptual end, okay, without considering the linear superposition and homogeneity, etc., y equal to x plus k is a linear system we may consider. Okay, but this is not completely linear, in sense that it is as per the superposition and homogeneity, it doesn't satisfy the conditions of linearity. Okay, so it keeps, say for example, if I have 10 x1 to x10, like the summation term adds by 10 times, okay, in the response, but it won't add when I directly give y10 of n kind of thing. Okay,
Yes.
right. Yeah, so now let us move on to another example. So say y of n is equal to okay. So is this system linear? This is not linear. The earlier one is not linear. So now example 2. Yeah, is this system linear? I need an answer from another probably army officer. So who has answered before? Pradeep or Girish?
Pradeep has answered, sir.
Yeah, fine. So request Girish to answer now. Girish is there?
Yes, sir. Yes, sir. Not sure,
Yeah,
sir.
please answer. Not sure. Okay, test it. If it is not sure, quickly I give 1 minute to you, each of you. I think some of the students who might have previously done good number of exercises will be able to tell very easily whether this is linear or not. But I will give you 1 or 2 minutes. Quickly check, verify at your end and tell. Yeah, some of you can answer. Any student is fine. Some of the MTech students who have regular MTech students who have not answered before, if they can answer, it is good.
Linear, sir.
It is linear. Okay, why is this linear? So because same thing. So if I give x1, it will be summation of x1. Okay, x2, summation of x2. A case doesn't change. What the system is doing is, see, if I will give a simple example for this system. Okay, see, to answer some of these things, you can take a freedom to design your own simplifications. Okay, k minus 5 to 5. How many samples I am adding now? K minus 5 to 5 means how many samples I am adding now? I'm just trying to understand the operation of the system. Huh?
10 samples.
sir.
10 samples?
11, sir.
11 samples I am adding. Okay, so let this AK be 1 by 11. Okay. Oh, including 0, there are 11 samples. Okay, so 11 or 12. Yeah, 11 samples. So if I'm let this AK, all AK be 1 by 11. Okay, just for simplification or for better understanding of the system. n minus k. So what does this system, if I explicitly write like this, what is this system doing now? What is this system doing? Quick answer is required. What you people are thinking?
Average.
Yeah, it is averaging what samples? Which samples is it averaging? Which are the samples it is averaging?
X of n samples, sir.
So if there are some samples like this, okay, if there are some samples like this, say this is 0 sample, okay, and this is -5, assume that this is +5, okay, and then probably 6 sample and so on, there will be another samples. The samples may be of different lengths and so on, okay. So I have not plotted all samples, okay, just plotting here and there. So let this be 10 sample. Let this be say -9 sample or whatever. Okay. So at this location, when n equal to 0, so y of 0, if I want to find which samples I'm averaging. So I just want to find y of 0. Okay, which sample is the system averaging? So this is x of n. Whatever I have plotted here is
X of n, sir. X of n samples are being averaged.
That is fine. Is it averaging all x of n samples?
No, only from -5 to +5.
Right. So is it correct to say that -5 to +5? Which x of n samples is it averaging? Tell very precisely.
X of -5. X of -5 to x of +5.
Okay, x of -5 to x of +5 for y of 0 only. Okay, if I ask y of 0, then it averages from, okay, so then it averages from x of -5 to, okay, x of +5, okay, and then averages and puts it. Okay, so and then the y of 0 is obtained. Fine or not? But if I want to find, say for example, so let this be -6. Okay, I want to find my y of 1. Sorry, y of -6. Then which samples will it
n
average?
plus 5 to n minus 5.
Right. So that is very correct wording. It is averaging n plus 5 to n minus 5 samples and putting the value. Fine? Is it fine or not? Okay, so that is fine. So this is the system. So what I'm trying to give is this is all the systems that I write here. You should be able to understand these mute talking. Yeah, request to mute if you people are not talking. Yeah. So all the systems that we write, you should be able to understand verbally what those systems are doing to understand them better. Okay. So here, so the previous system is whatever you give as input, it is adding u of n plus 1, some constant quantity to the input. Okay. So this system, what is it? It is just averaging and putting at a center value. Now, if I want to check for linearity, what do I do? I say follow the same procedure. X1, Y, so X1 of n. Okay, if I give as input to the system, what I get is Y1 of n. Okay, Y1 of n will be explicitly, if I want to write K, AK doesn't change because this is like a constant, as I said here. Okay, AK, X1 of n minus 1, n minus K. Okay, so the input signal had changed. That's why only signal had changed in the output. But the operation is same. Similarly, you can write Y2 and then you can write alpha 1 times R X1 plus X2 and then you can see its output. Finally, the Y3 you can write in terms of AK, you can take common and so on. You can finally see that this system is linear. Okay. I request you people to check because X1 of n plus X2 of n, okay, if you give as input, okay, you can see that the output Y3 of n you get, okay, will be equal to, okay, Y1 of n plus Y2 of n. Okay, so you can see that this is correct. Okay, so this is correct here. So this will become linear system. Fine or not? I
Yes,
hope
sir.
this is clear. Yeah. So now we
Yes,
will
sir.
move on. Okay, you discuss on like you do on the other examples and tell me if you find any difficulty in there. Okay. So now we will discuss on the time invariance. When the system is said to be time invariant, I think you people may know, right? So can some of you tell?
Sir, if there is a
When
delay
the system is, yeah.
if there is a
If there
delay
is
in
some
input
delay, okay,
in input, then
right.
corresponding delay will appear at output, sir.
Output. Okay, so that is called time invariant system. That means, what does it verbally mean? What does the time invariance verbally mean? I request another student to answer. Yeah, I request another student to answer.
If the output does not depend when system is
Yeah, output does not depend.
on when the input was applied, the time of the input.
Right. So that means that, see, I can say if I ring a bell. Okay, so if I ring with some kind of stick, so I assume that every time if I ring with same intensity, it will ring exactly the same sound. Okay, so the sound that it rings is in some sense doesn't vary with time. Can you give an example of time variant system? Any example of a time variant system? Give some examples. I think you should be able to give, right? Any system is fine. Say human, for example. So humans act as a time variant systems or time invariant systems?
Time invariant. Time variant.
Time
system.
invariant.
Variant.
Yeah, time variant systems.
Yeah.
Okay, if you ask me now, there may be some answer. If you ask me, so at some other, say during night, some 10 o'clock or something like that, another answer may come. Okay, or even now, if you ask 2-3 times, I will give 3 answers. Okay, like that. So usually, the behavior changes with time. So it is time variant system. Similarly, there are many, say, for example, computer program, for example. It is time variant or time invariant. If I make a program in computer and execute it, is it time variant or time invariant?
Invariant, sir.
Invariant, sir.
Time invariant.
Invariant. It will give same answer. Okay, but if I generate random numbers, so I have a random number generator. If I generate random numbers, so do you think every time I get same numbers or different numbers?
Different, sir.
Different
Yeah, so
numbers.
like that. So anyway, these are
Different
just
numbers.
examples. But I think in systems, in any of the electrical systems or electronic systems, or any other systems, the time variance or invariance comes, especially time variance comes mainly because of the randomness or the noise. Okay, so if there is no noise and randomness, they mostly behave in a systematic way. But there is always a noise and the randomness involved in modeling the systems or in the physical systems, real systems. So they have smaller or larger time variant components. Okay, but some of them are many of them can be modeled as time invariant systems with some approximations. Okay, fine. So now what we are doing for checking of time variance and invariance, we give a delayed signal. Okay, x of n minus n naught. N naught can be positive or negative as well. Okay, delay or advance. Okay, so we can give either of this shifted signal and then check that the output I will just check. So if I give the delayed signal, what I see is yd of n only. But now what is the check here? Is this equal to y of n minus n naught? Okay, this should be very clear. When I give the question, if you don't directly write, okay, y of n minus n naught, x of n minus n naught, output is y of n minus n naught, you won't get anything. Okay, you should first give input delayed and you should see what is yd of n. without looking at y of n minus n naught. Okay, then you should compare whether it is equal to y of n minus n naught. Okay, so let us take one or two small examples. Okay, so now x y of n is equal to, let us take same example, x of n plus, okay, u of n plus 1 or u of n plus n. Okay, for simplicity. Is this a time variant system or time invariant system?
Time variant system, sir.
Time variant system, right?
Yes,
So
sir.
how do I do it? So I request another army officer to help me for these steps. So I give x of n, okay, and output I get is y of n anyway, which is there. Now I give, what should I give as input? I think Manmeet, if you are there, you can tell. Yeah, Girish is also fine.
He is not present, sir. Manmeet is not.
Yeah, you can
X
tell.
of n minus 1, sir. No.
N naught I will give. Okay, N naught can be any number, 2 or even minus 2 or whatever. And output what I get is, so let this be x d of n. Okay, and then y d of n I should get first. Okay, y d of n is what? I will try to write from here. Y d of n will be in terms of input x d of n. Okay,
Yes,
plus
U of
plus what? Plus
U of n.
u of
N.
yeah. Okay, but because what is the system doing? You give anything, it just adds u of n. That is the operation of the system. Okay, so now similarly, this y d of n, if I expand, x of n minus n naught, okay, plus u of n. Is this equal to? Is this equal to y of n minus n naught? Huh? Is this equal or
No,
not?
sir.
It is
No,
equal.
sir.
No,
No,
sir.
sir.
So not equal. So it is
No,
not
sir.
time variant. No. Okay. So not a time variant, not a time invariant system. Is this fine?
Yes, sir.
Okay. Fine. So we will move on. So now let us. I will give you another example. Okay. Y of n is equal to, so this also probably I think of similar lines. So we will, let us take the same example that we have taken above. So y of n is equal to summation x of n minus k, ak, k equal to -5 to 5. Okay. Is this a
Time
time
invariant,
variant
sir.
system or time invariant system?
Time invariant, sir.
It is
Invariant.
time invariant.
Time invariant.
Yeah. So at any time, if what I will do, it just averages at that point of time. What are all the samples? It does the same operation. The output may not be same, but the operation is same. Okay, behaves in a same way. Okay, so it is time invariant. Okay, yeah. Anyway, you can check it. Okay, so now let us move on to the discussion on the other properties. So what is causality? Causality of a system.
Non-anticipatory system, sir. Depends only on present input.
Yeah. Y of n depends on present and past.
Past and-
Of what? Past? Complete the definition.
Inputs.
Inputs. Okay. It depends on present or past inputs. Okay. So or in other way, how do you or do not depend on the
Future values.
Future inputs.
future. Yeah, you give some examples? Anyway, I am giving my examples till now, till so far. Can one of you tell example for a causal system and one of you tell example for a non-causal system?
So y of n equal to x of n minus 1.
Okay, fine. Is this causal or non-causal?
Causal system.
Okay, fine. So you give very trivial example. When I ask you to give some challenging example. Little difficult example. Okay, any other example for a non-causal system? This is causal. See why this property is important, causality. Why this property is important? Hello? You people are there?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yeah. So why this property is important?
To check whether the system is physically reliable or not.
Realizable or not. Okay. All the real systems work only based on the inputs that they received so far till then. Okay, at that point of time, but not based on the future things. Yeah, except there are some systems like humans. Okay, who will also anticipate and work. But the physical systems mostly work considering the things in hand. Okay, so usual realizable systems that are realizable also are in that manner. Okay, fine. So now give example of a non-causal system. Can one of you give an example of non-causal system?
2 power n into x
X
of
of
n
minus
plus
n.
X of
X of minus n also non-causal.
okay, x of minus n. Very good. This is also non-causal. Okay, why is this non-causal? I request any other student to answer. Why is this
For
non-causal?
negative values, it gives
Yeah,
positive.
for negative values of
gives
so when say when you consider negative indexes of n, okay, they depends upon their like at the output of positive indexes depends upon the negative indexes, fine, but some the output of the positive indexes depend upon the negative indexes of input. Okay, fine. So it is non-causal like that. So what about the system that we discussed before? Is this system y of n equal to summation? Is this a causal system or non-causal system? Y of n equal to AK. I request any other student to answer. Okay. Anyway, -5 to 5. Okay, causal or non-causal? Request
non-causal.
say non-causal. Fine. So I request students who have not answered to answer. So give them some time, and they also actively tell. Okay, because these are all the very elementary things in signals and systems and signal processing, right? You may have studied reasonably good number of times in different ways. So fine. So but for completeness, I am discussing. Okay, tomorrow you should not say that I am not very well aware of causality and linearity and so on. Okay, yeah. Next, stability. Also, can you tell actually when the what is the definition of stability of a system?
Stable input, the system.
For a bounded input.
Yeah, for a bounded input, you expect to get a bounded output. Okay, so now y of n, if I write, say for example, so bounded input gives a bounded output, then system is stable. Okay, so what do you mean by that? Say for example, I will give you some examples here. Okay, with these examples we will try to discuss. Say x of n minus k or whatever. Yeah. So is the system stable?
No, sir.
Similarly, I make you one. It is not stable. So or
Not.
yeah. So so even this system, whichever I have considered before, what is that system stable? Is the system stable or not? Among the
Stable,
systems,
sir.
Stable,
this
sir.
is stable.
Stable, sir.
Yeah, this is not stable. Okay, so if I assume that all the inputs are bounded, what will happen? C, assume that inputs are roughly bounded by C, a maximum of all these inputs. Then say this will be 11 times C. Okay, and into AK. So I know I can specifically tell that the output is also bounded or a finite number. Whereas here, even if everything is C, I am adding for infinite times. If they are non-zero for infinite times, then it will not be bounded. Okay, so that is how why system stability is important. The name itself indicates why system stability is important.
So to know if the system works properly for noise, if noise comes or not.
Yeah, to know if the system works
Properly if noise is present.
Okay, if the noise is present is fine. Okay, so that is one nice way of telling. So you mean to say that noise is present. So why do you say it so? Why do you want to bring in noise?
Sir, if there is any change in input, if the output changes very, the change in output is very high.
Right. Okay. So in some sense, what you are trying to say is, if there is a small change in input, if there is a very large change in output, okay, so then the system is not stable. Okay, so that's what you are trying to tell.
Yes.
Fine. In some sense, whether it behaves in a like without exploding at any point of time. That's what it ensures. Okay. So now move on to the discussion of linear and time invariant systems. Okay. So what many of the practical systems can also be modeled as linear and time invariant, approximated as linear and time invariant. Even though many of the practical systems are non-linear, they can be approximated as linear and time invariant. And there is a elegant theory that helps us to analyze once we approximate it as a linear and time invariant systems. That is why mostly linear time invariant systems are well studied. Okay, so now let us see, let us take a system, assume that this is linear time invariant system. Okay, and here again x of n as input and y of n as output. Okay, so now tell me what additional benefit do we get if I specify initially itself that the system is linear and time invariant? Yeah, I need some answers. Hello? You are there or not?
Yes, sir, we are there.
Yes, sir.
Yeah. So wish to get some answers. What additional benefit are the advantage we get if I say that the system is linear and time invariant?
It is easier to represent such a system, maybe graphically also.
Okay.
Graphical representation is also easy.
Okay. So you will go to the graphical representation first if we have some easy representation of this system. So how do we represent the system first? So what advantage do you think we will have if I say that the system is linear and time invariant?
Sir, even if you know the output for one signal, we can determine for other inputs also.
Okay, very good. So you mean to say that if I analyze the system behavior or output for some standard signal or signals, I will be able to tell its response for many of the signals. Fine, is it correct?
Yes, sir.
Yes, sir.
Right. So what is the standard signal you would like to consider as input and analyze? Say if I give you choice, okay, take just one signal, a standard signal, and you use my system and find its response, and then you should be able to find response of it for any of the signals later. What signal will you consider?
Impulse,
Impulse.
sir.
It is
Impulse.
impulse. Very good. So impulse
Impulse.
signal we take. Okay, so let us take impulse signal. Yes. Okay, so if we take impulse signal, give as input, what I get at the output?
System response.
System response for
Del of
system
Impulse input.
so system response for
impulse.
yeah, for impulse I will get. Okay, so it's response for impulse. Okay, what is this called? Okay, impulse as input to system. Okay, gives response for input impulse or impulse input. So what do we call this as? Oh, what do we call this as?
Response.
Impulse.
System response.
Response for impulse input. Okay, so what do we call this as? Impulse response.
Response.
Okay, so this is very important thing. I see that in the class when the things are all clear, many of the students will define it, but even in interviews especially, even this simple thing when we ask, usually people struggle to tell what is impulse response. Okay, so what if we just give input as delta n, okay, for a system of LTI system, okay, in fact for any system it is impulse response only, but for an LTI system there is a benefit. What I get output is h of
Impulse response.
n. Okay, we denote it as h of n. It is transformation of the system to delta n. Okay, so this is impulse response. Okay, fine. So now see, you said if I give you delta n, you can tell the response of any other inputs x of n. So how do you tell it? So you said if I give delta n and its impulse response, let it be h of n be the response of the system for input impulse. Okay, impulse input. So and I just named then it as the impulse response. Okay, so if h of n equal to transformation of say the system response for delta n, then only I will call it as impulse response. Okay, so now if I get this, using this you said you can do a lot. So now how do I find for any x of n output? Tell me.
X of
I
n
just
can be
want output for
decomposed
x of
into
n, any arbitrary x of n. How do I get it?
X of n can be decomposed into impulse signals.
Yeah. So I want to get the x of n if I give as input. Okay. So what is y of n? I want to get. Okay. Given this. Given this information. To do that, what do? We decompose x of n as in terms of
H of n.
in terms
Impulse.
of what? Impulse. How do I decompose? So I request another student, like different students to answer. Okay, because if say I'm not able to see your names and all, so I request you people to like keep wait for other students to answer, and at the same time I request other students to proactively answer. Yeah. Tell actually how do I split in terms of impulses?
Summation of k equal to minus infinity to infinity.
Okay. So who is telling?
Sir, Harshvardhan, sir.
Huh?
Harshvardhan.
Harshavardhan, okay. You did not tell before?
I told, sir.
Okay. So I want someone who has not told before to tell. Just give me a 1 minute pause. Yeah. So request to tell. No.
X of k
Request.
into del of n minus k.
Who is this? Niharika?
Yes, sir.
You didn't tell before?
No, sir.
Okay, fine. Okay. So this is, what should I write?
X of k
Okay.
summation x of k into del of n minus k.
Del of n minus. Okay, very good. So see, this is fine. This is so what I'm doing in this process. So if I have, say, for example, I will just try to pictorially put it. Okay, whatever you have told here directly. So I will try to put it pictorially here. Okay. So now assume that I have a signal like this. Some signal like this. Okay, I may start from 0 or anywhere. So I have an impulse signal here. Okay, so this is height is 1. So some that respectively the other heights are. So this is delta n I have with me. Okay, 0. And this is x of n. So through this decomposition, what I'm doing? What is that I'm doing? Can one of you tell quickly? Through this decomposition, what is that I'm doing? Another student, quickly please tell. So Anjana, can you tell? Is she there? Or any other students? Manmeet, you can also tell. So through this operation, what am I doing? This is x of n and this is delta of n. Okay. I
So
request any other
multiplying
student to answer. Yeah.
multiplying x of n with del of n and then summation.
Okay. See, I will just write something here. X of k into delta of n minus k. Okay, and I say that k equal to 5 in this case. Okay, then what do I get?
Sampling, sir.
What do I get?
X of 5 into del of n minus 5.
Okay, you are telling again in words, in say in mathematical terms. I want in words. What is this? It is picking. What is this? This operation is doing.
The sample at n equal to 5, sir.
Yeah, it is picking the sample. This through this delta function, I'm picking each individual samples. Okay. By shifting this delta function, I am sampling at different instances. So n minus k, I am sampling here. Through this, I am sampling. Which sample I am sampling? Sampling n minus 5, fifth sample. Okay, or fifth sample. Okay, because I think n minus 5 means it is fifth sample. I am sampling fifth sample. Fifth sample from x of n. Fine or not? Okay. Similarly, each sample is sampled, but its location is kept as it is. So the output, if I see here, this will be say if so some values are there. So if this is 0, only fifth sample, what it is, whatever it is. Okay, this is what is now this x of 5 into, correct or not? This is what I am picking from this x of n. Okay, so I assume that 0, 1, 2, 3, 4. So there is a fifth sample as well. Assume that something like this. Okay, I'm just picking that sample. Correct or not? So I'm breaking this, decomposing this x of n into each sample by delayed versions of the impulses. So I'm using different time variants of impulse function and scaling it through appropriate values of the magnitudes of x of corresponding sample to write x of n, the whole signal of x of n. Fine. Now tell me. So this is fine, starting, very good starting point. Okay. From this, what I want to do? I want to say that I can find response for this, any signal like this for this LTI system. How do I do it? How do I do it? Can you please tell quickly? With this, we will wind up our class. Okay. So the subsequent things we will discuss in the next class.
Yes, sir. We need to do convolution with the.
No. How do I got convolution? I can't get convolution and all now. I only have this x of n with my hand, in my hand. I give this x of n. So now you are allowed to take this x of n. Okay. You are allowed to take this x of n as input to the system. Okay, that's only I have with me.
Some of the responses. By summing their responses.
Okay. Yeah, fine. Summing the responses, I will do. LTI system I have with me. So x of n I give. X of n, I can write x of n as, okay, so xk, like you people have decomposed, delta of n minus k. I can write like this. Okay, I will give k equal to minus infinity. I can give this as an output. I want to get y of n explicitly. What is this? Okay, is my question, but I don't have it. So what I will do now, but I have with me, what is, for delta n, what is the output? So if I give delta n as input, okay, I know that the output is h of n. This is what I know. This is known. Okay, this is unknown. So how do I do it now? So I will write y of n is equal to some transformation, okay, are sending to this sigma x of k delta of n minus k, right? Then what do I do? What is the next step I will do? What is the next step?
Sigma k is equal to minus infinity to infinity x of k into transformation of delta of n minus k. That is.
Why? Fine, very good. So who has told that? Can you please tell how, what property enabled me to do this? Why I am able to do this? It's fine. It is very good. So I have taken summation out and then put the transformation inside because x of k is a constant. Okay. And then n is here. So delta n only is a time varying quantity that is given as input to the system. So it can write transformation of this. This is perfectly fine. But given some property, this is perfectly fine. Otherwise, it is not. What is that property?
Homogeneity.
The system is linear.
Yeah.
Sampling
So both
property.
linear, both linearity and homogeneity. In sense, homogeneity and superposition. So using the linearity property, I can write this. Okay. So using, so first I should use using the linearity property. Okay, I can write this. So because I can take, I can interchange. Say if I have two signals, say it is essentially alpha 1 times delta of n, okay, plus alpha 2 times delta of n minus 1. Okay, so these are like two signals. Okay, and so on. So if I give as input to the system, what I will get is output is alpha 1 times whatever is the output h of n, okay, plus alpha 2 times the h of n minus 1. Okay, I cannot write this yet, but at least I can write transformation of. Okay, yes or no? So at least till here I can write. Okay. Sorry. Yeah. So transformation of I will write rather than h here. Okay, for the second one. Okay, till here I can write. Yes. So this is what is enabled me to write like this, because it's the all summation of different delta n's. I can write like this. Okay, fine, good. So what is the next step? What is the next step?
X
You
of
wish to
k
get
into
another
x.
answer from another student. Yeah, no, same student. I
X
think.
of k
Using
into
time
x of n
invariant
minus k.
property.
So what should I get here?
H of n minus k.
H of
H
n minus
of
k.
n minus k. Okay, when can I write this H of which property enables me to write this again?
Time invariant property.
Using time invariant property. Okay, using time invariance, I can write like this, because time invariance enables me to write transformation of this delta of n minus k, whatever, okay, is equal to h of n minus k. Okay, so only time invariant property, if it holds, then I can write like this, because I know that delta n is h of n, output of delta n is h of n. Okay, fine. So this is now y of n. So this y of n now is summation over in minus x of k into h of n minus k. So what is this? Can be written as in simple form, in simple terminology. We write x of n. What is the symbol I have put here?
Convolution.
Convolution. Okay. So x of n convolution with h of n. Fine. So see, where does this convolution operator generated from? See, in the introductory classes, I told about correlation, right? So correlation, what is the origin of correlation? Why did we define correlation and so on? What is the origin of correlation?
To find the similarity.
Very good. To find the similarity, we use correlation. So that is the origin for correlation, definition of correlation. Whereas what is the origin of convolution? So convolution operation, okay. What is the origin for defining this operation, convolution? I request some students to answer.
LTI property, linear time
Yeah, if the system is given to be LTI, okay, then if you just know the impulse response or the response of the system to impulse signal, then this process of finding response to any arbitrary input, okay, x of n, is through convolution of x of n with respect to the impulse response of the system h of n. Fine. Is this clear or not? See, you may know the relations, but this understanding is very much necessary. Okay. So the convolution itself originated from systems. Okay, system signals and systems theory. Okay. If you want to find response of a linear time invariant system, that's where the convolution has come. It automatically stamped. So we define this itself, okay, this operation itself as convolution. So it's like defined as. So it's, you can consider this is defined as. Okay. So there is no existence otherwise for convolution. Okay. But convolution is important, because if you just know the response for delta n, you will be able to find the response for any x of n. Okay, fine or not?
Yes, sir.
Yeah, I request the army officers to tell, is the discussion clear?
Yes, sir.
So weak yes or strong yes?
Yes, sir, strongest.
Okay, fine, good. Okay. So this operation itself is convolution. What is this operation doing? What is this within this operation doing? So you see that, so we will see what it does with a small example. So I will not spend the whole example here, but I will now verbally tell what is it doing. So in the next class, we will see 1 or 2 examples for this. Okay. So say, let us understand this expression. Okay, so y of n is equal to summation k equal to minus infinity infinity. Okay, x of k h of n minus k. Okay, so first understand actually what is this h of n minus k. So if you have h of n, okay, so this is the original impulse response of a system. Fine. If you have delta n, from that you will get the h of n. But if I want to write h of minus n, what is the operation I should do? How is it related to h of n? If I give you anything as h of n, okay, if this is h of n, okay, what is h of minus n? What is h of minus n?
We have to use a time reversal property.
Yeah, time reversal for h of n or flipped version. Okay, flip in time, flipped version of h of n. Okay, in flip in n. Okay, so it's time reversal of h of n. Okay, so is what is h of minus n. Then see, if I have, so I will write now h of n minus, say if I write anything, so n naught minus n. What does it mean? Or say for example, if I write h of n minus n naught, what does it mean? What is h of n minus n naught?
Shift by n naught towards right.
Yeah, it is delayed version. Delayed means
Delayed
right.
version.
Okay, so delayed n naught delayed version of h of n. Fine. Now can you define what is this doing? So h of it is
Advancement.
yeah.
Shifting
So I
of
can
order.
write this in like this. First, okay, time reverse. And delayed. Okay, so if I write say h of minus of n minus n naught, okay, then first operation is time reversed and second operation is delayed by n naught. Fine or not? So if I just go by our typical writing of operations, first operation is time reversal, second is minus n naught it comes if I take common, okay, that only affects n and delayed by n naught. Fine. So it is placed at n naught in some sense, either this side, okay, it is delayed by n naught and then time reverse. Sorry, it is time reverse and then delayed by n naught, or it is now located at n naught of with time reversal. Fine. So there are two operations essentially. We will see exactly where these things fall. There are two operations. One is time reversal. Another is shifting. Okay. If you don't bother about delay or advance, okay, this h of n minus k is placed at different n locations, and it is time reversal version of h of so h of n, because k is varying from minus infinity to infinity. Okay, this whole signal will come and it is placed at different locations of n after time reversal. Fine. Is this understanding clear?
Yes, sir. Okay.
So what I give is, now I will just give two examples. I will not solve it now. Okay, you do and come back. Okay, we will discuss in the next class. These two examples I will just give and leave. Okay, so you try to do it and come back. Okay, so fine, this is the impulse response. Okay, and this is the signal. What we want to find? Output of system described by h of n for x of n is what? Okay. So what essentially I asked here? What did I ask here in writing that much? Huh? What did I ask?
The output of system.
Yeah, that is fine. What is that I asked? So in terms of notation.
X of n into h of n.
Convolution.
Convolution.
Yeah, convolution I asked you to do, but after doing that, what will you get? Y of n, right? Okay, so essentially asked for y of n, correct or not?
Yes, sir.
Yeah. Okay, just a minute. Sorry. So x of n, let it be a power n u of n. Okay. And then h of n, this system, linear and time independent system. Okay, where h of n is equal to u of n minus u of n minus 10. Okay, I have given some specific h of n, and what I wish to get is what is the output. Okay, same things are same. This is example 2. Okay, you solve and come back. Anyway, we will discuss briefly in the next class and move on to the discussion on probably if anything else related to LTI systems. If you wish to discuss, we will discuss a little bit. Then we will move on to discrete Fourier transform. Okay, discrete time Fourier transform. Okay, we will move on to the frequency domain analysis. Okay.
Yes.
Is this fine?
Okay, sir.
Yeah, fine.
Fine, sir.
So we can, if there are any questions, we can discuss. Otherwise, we will close the session. Any questions? Any questions you want to put? Questions or clarifications or anything to discuss? So anything to discuss or not? Shall we close the class?
I think we can close, sir. No one is responding.
Yeah, fine. Okay. Thanks then. Thank you. So see you on Friday. And meanwhile, I will try to send the notes of discrete Fourier transform, discrete time Fourier transform. Okay. So that we can start discussion on that from the Friday's class. Mostly. Yeah. Thank you. Thank you all. Bye.
Okay, sir. No, welcome, sir. Thank you, sir.